Thanks for watching. Today we're going to do filters, and in particular I'm going to run through Patrick Massot's filter exercises, which I haven't looked at, I must confess, other than during his lecture. We're going to run through Patrick's filter exercises. So what's a filter? I mean, definition of filters. Maybe we should have a look at what a definition of a filter is. So we could start by, let's do that. And now can we go to filter? Is that a thing? Let's see if we can find what a filter is. Where are filters going to be? Do you know what? Here's the best way of doing it. Let's right click on filter. Great, here we are. So here's a filter. What's a filter? A filter on a type alpha is a collection of subsets of alpha which contains all of alpha and is upwards closed, so if something's in the subset, then anything bigger is in the subset, and is stable under intersection. This is finite intersection. So you can see the definition of filter is a set of subsets of alpha that contains the whole space. If X is in and X contains Y, then Y is in, and if X and Y are in, then their intersections in. So it's a bit like a topological space in some. It's a very similar sort of definition, a collection of subsets with some property, but it's not a topological space. It's something else. So let's get going. The first exercise here. So we have 11 warnings, which presumably correspond to 11 sorries. So the first example of a filter is given a random subset of alpha. So this is the filter generated by a set S, by a subset S of alpha. You're in the filter if and only if you contain S. There. It doesn't like that. Let's move that. Let's move those comments over here then. Right. So what is going on here? We're trying to define the principal filter generated by alpha. I mean, one interesting thing. Bingo. We're trying to define the principal filter generated by alpha, and generated by S, and it's all the sets containing S. And the first thing we need to do is prove that alpha itself is contained in this set. So by definition, what does this actually mean? What have we got to prove here? We've got to prove that this is what we've got to prove. When you unravel all the definitions, we've got to prove that whatever our set S is, it's contained in univ, which is the set of all, which is alpha. So that's going to be called, that's the sort of thing that's going to be in the library, right? That's going to be called exact subset univ or something. There's my guess. There we go. Exact subset univ S. So that's the first proof of this. And actually, let's have a look at this subset univ. If we print it up here. There we go. Look, we can see that subset univ is tagged with simp. And so my guess is that this entire thing will be solved by simp. There we go. So that's solved that. Now what? Set of superset. What have we got to prove? We've got to prove that, so this is the axiom for filters that says if I'm in the filter and then something else is bigger than me, then that other thing is in the filter as well. We could try simp, right? We could just, it doesn't like it. So let's work out what this says. So intros, I don't know, I like capital letters for my intros A and B. So we've got two subsets A and B, and we know, what do we know? Intro, we know HA, we know something about A. We know that A is in the set of sets that contain S. So why don't we desimport HA? Let's just see what that says. There we go. So we've got A and B as subsets of alpha. We know that S is a subset of A. We also know A is a subset of B. Intro HAB. And our goal is to prove that B is an element of the sets B is an element of the set T such that S is a subset of T, and so just simplifying it again, that means we've got to prove that S is a subset of B. So the dust has cleared now, and we can see what the problem is. We know that S is a subset, so S, A, and B are sets. We know that S is a subset of A, and S is a subset of B. No. We know that S is a subset of A is a subset of B, and we need to prove that S is a subset of B. So that's going to be that's going to be called transitivity, right? If I do library search, maybe library search will do this for me. There you go. You see, it's in the library. So that's the proof of that. If I put a comma, there we go, goals accomplished. So that's the proof of that. And in fact, I wonder, we probably don't need all of these simplifications there. And this is an exact there. And so in fact, we don't really need tactic mode at all, do we? We could just say intros lambda A, B, HA comma, subset dot trans, HA comma. We can get rid of all that. And there we go. Everything's compiling, and there's our term mode proof. So now what? Again, so this axiom here says that, what are we trying to prove? Intersection of two sets in the filter is in the filter. That's what we're trying to prove, i.e. If S contains A and S contains B, then S contains A intersect B. Okay, so let's go. Intros A, B, H, A, H, B. And so now let's do dSimput star. Let's tidy everything up. There we go. So S is a subset of A, S is a subset of B. We've got to prove that S is a subset of A intersect B. And again, that's bound to be something that's in the library. And it is in the library. There we go. Exact this. And we probably don't need to simplify anything. And I could write that in tactic mode. I could write that in term mode if we like, but let's not bother. So there's the proof that the principal filter on a set is a filter. So here's another example of a filter. Here's a filter on the naturals. And the sets are what? This filter on N has as elements the sets which contain the interval. It's this, isn't it? It's A infinity there for some A. The idea is that you're in if and only if you contain every single sufficiently large natural. Okay, and this is slightly more interesting because there's an existence in here. So univ sets. So what have we got to prove here? We've got to prove that there exists an A such that for all B, if B is at least A, then B is in the set which contains everything. But the goal, I mean, so this is obvious, but at the end of the day, the goal is an exist statement. And so we get rid of an exist statements with a use. So I could use 37. I would imagine I could use anything. So let's use 37. And now I've got to prove that every natural which is at least 37 is in the set of all naturals. So intros B, B and HB. The advantages of term mode are that it somehow, computer scientists like the library to look far. I mean, it's just shorter. It's less code. That's in MATLib they seem to like term mode because it's less code, and especially when you're proving things which are kind of mathematically trivial. I mean, look at this. I've now got to prove, you know, at the end of the day, I've got to prove that B is in. I've got to prove that I've got to. I mean, I've got to prove that something is in. This is going to be. Yeah, let's apply mem univ or something. Apply mem univ. There we go. But they certainly wouldn't have. I mean, so they would do this, right? 37, comma lambda B HB memuniv B or something. There, you see, there's they just like it taking, you know, they just like it taking one line. It just somehow looks more, I don't know, looks more professional. This could, they probably even like this, right? There. Sets of supersets. So what does this say? This is the one that says intros A B H A H A B and dsimp at star. Let's see what we've got to do here. So HA, so A and B are subsets of sets of naturals. HA says that for there exists a little a such that everything bigger than little a is in big A, and we know that A is a subset of B, so the same A will work. Great. So in fact we can take this H, we can use rintros here, right? We can do rintros, and instead of this we could do this, A H A A. I would imagine, there we go. So now we've got our little a, and great. And so now the question is, what do we use? And we use the same a. We know if every natural at least little a is in capital A, and A is a subset of B, then every natural at least little a is in capital B. So let's use A, and then we can do intros B and HB. And now we've got to prove that B is in B. And this is, I always like this. This HAB, this is a function. This is kind of cool. This is a function that takes an element X and a proof that X is in A, and it outputs a proof that X is in B. That's what A is a subset of B means. It means every element of A is an element of B. So we can apply it. Even though it doesn't look like a function, it is a function, so we can apply it. And now our goal is to prove that this, and now you see that was the conclusion of HAA, so we can apply that as well, HAA. And now we have to prove this, and so this is exact HB. So there's that, and now here, oh well, this has got some content. This one here, so intros, let's call them X and Y. X, Y, because I'm sick of saying little a and big H. HX and HY, and let's dsimp. So what's the question here? We've got two subsets of the natural numbers, and we know that every natural number bigger than A is in X, and every natural number bigger than something else also called A. So this is not ideal, right? Let's give these things names. We're intros A X Y and then A H A. And then BHB. Let's try that. Now let's see what the question is. So we've got two sets X and Y. We've got two natural numbers A and B, and we know that every natural number bigger than A is in X. We know that every natural number bigger than B is in Y, and we've got to prove that every natural number bigger than something is in X and Y, and so that something is clearly going to be the max of A and B. So let's use max of A and B. There, and so now let's intro C and HC. So now let's say C is a natural and C is at least A and B, and we've got to prove that C is in X and C is in Y. And clearly the strategy is we've got these, you see, we've got a method for proving that things are in X, we've got to prove they're at least A. We've got a method for proving that things are in Y, we've got to prove that they're at least B. So why don't we split, because we've got to prove two things here. I might come back to that split. So now we've got two goals, and the first thing, we've got to prove that something's in X, so let's apply HA. Let's tidy it up. So now we've got to prove that A is at least C, and you see that's going to follow from the fact that C is at least the max of A and B. So C is certainly. So this is probably. So let's apply LE. Let's apply transitivity of less than LE trans something and then HC. Great. And now I've got to prove that A is less than or equal to the max of A and B. And that the simplifier will know that, presumably. Does the simplifier know that? No. That's going to be called LE max left. There we go. Great. And so this proof here, we're just going to be able to copy, right? Apply HB, apply LE trans blank HC, then it's going to be apply LE max right. LE, let's get rid of that, sorry. How about that? There we go, goals accomplished. Great, so we're now down to, so there's a filter on the naturals. Oh, this exercise is slightly more tricky. We should probably keep it for later. Let's go nuts. Great, so what's going on here? The neighborhoods of IC. So the neighborhoods of X, what is a neighborhood of X in the real numbers? It means a subset of the real numbers whose interior contains X, i.e. a subset of the real numbers which contains an open interval around X. Great. So Y is the real numbers, such a thing. And my guess, so we need to find an interval around the real numbers which is contained in the set of all real numbers. So why don't we take an interval of radius 37? So use 37. And now I've got to prove split. So what have I got to prove here? I've got to prove that 37 is bigger than 0. So that's norm num does that. Norm num does calculations with concrete numbers. And now this one says the open interval. This is just notation for the open interval. The open interval from x minus 37 to x plus 37 is a subset of the set of all real numbers. So we could do intros x, hx or something. Let's do y. Intros y, hy. And now I've got to prove that y is in the set of all real numbers. So that's apply mem univ. So that wasn't so hard. Sets of supersets. This feels very similar to this stuff, doesn't it? Look at this. Let's just copy this. Won't work, but it's close, right? Intros A, B, and now A, H, A. Oh, okay. So maybe we shouldn't copy this. Oh, I placed it in the wrong. I put it in the wrong place anyway. Maybe we should put it here. Oh, rotten luck. Let's try putting this here. Oh, this looks good. So we've got two sets of real numbers. We've got A. So this is probably epsilon. We've got epsilon and HA should probably be H epsilon. And what does H epsilon say? H epsilon says that there exists, oh, okay. So we could probably keep going. H epsilon 1, H epsilon 2. Let's see what we've got there. Okay, this looks good. And HAB says that A is a subset of B. Right, so what's going on? So we know that there's a little open interval radius epsilon around X contained in A, and we know that A is a subset of B, and so we can use the same epsilon. So let's use the same epsilon. And now we've got to prove, aha. So now things go slightly awry. So now firstly we should do, we need to prove that epsilon, we can just use H epsilon 1, right? I don't know if you can hear, but there's a very concerning beeping noise, which is something to do with something being in the oven. So I'm very unprofessionally going to go and take some bread out of the oven, I suspect. Right, I'll be back in 30 seconds. Okay. I opened it when you were asleep. Lovely. Right. Sorted. So now use H epsilon 1, great, because that's the proof that epsilon is bigger than 0. And now I've got to prove that this open interval, aha, so this is transitivity again, right? We know that the open interval is a subset of A, we know that A is a subset of B, and we know that the open interval is a subset of B. So this is just exact subset transitivity of subset. Is it called that? Is it subset dot trans? Yes, subset dot trans, and then it's H epsilon 2, and then it's HAB, and goals are accomplished. And then the intersection, we're going to have to use a min, I guess. We used a max before. So let's go, let's try this. This looks like a good start. We've got X and Y sets, and then A. So this should be an epsilon, epsilon, H epsilon 1, H epsilon 2, and then this could be a delta. An H delta 1 and an H delta 2 there. So we now have to prove, so what have we got here? We've got a positive epsilon and delta, and the open interval radius epsilon is contained in X, the open interval radius delta is contained in Y, and we need to find an open interval contained in X intersect Y, so clearly it's going to be radius min of, so let's use min of epsilon and delta. There. Now this should be easy. So Y is min positive. Well, okay, let's work that out. Why is this? Well, I guess is this min? Maybe this is called LT. This is, we shouldn't really have greater thans, right? This is show 0 is less than min epsilon delta, right? Lean prefers less thans to greater thans, and presumably there's a lemma that says LT min. Let's apply LT min. Yeah, you see that's worked, doesn't it? So now LT min must say there. You see, if A is less than B and A is less than C, then A is less than the min. So we now need to. It's H epsilon 1, H delta 1, presumably. And that's the end of that part. And now here, we now need to prove, oh golly, so now we need to get our hands dirty. So this is the last bit. This is presumably the bit. So now let's intro Y. Intros Y and H1. Let's see what we've got. So we've got to prove that Y is in both of these things. So maybe we should. So that's an and, right? We've got to prove that Y is in X and Y is in Y. So why don't we split? And why don't I go and close that door? So what have we got now? We've got to prove that Y is in X. And our only method for proving that Y is in X is H epsilon 2. So let's apply H epsilon 2. Let's tidy up. There, have I tidied up? Yes, no errors. Always good to have no errors. And now what do we have to prove? We have to prove that Y is in this open interval, and we know that Y is in this open interval. So now I'm getting, so this is just kind of looks trivial, right? So let's see if we can do, let's cases HY. Okay, and now we've got this stupid min. Can we cases HY with HY1, HY2? Hopefully this proof will, yeah, I see exactly now why Patrick was not happy about this. And so let's split this. We've got to prove that X minus epsilon is less than Y. You see, I suspect that linearith won't do it, but we could probably use transitivity on HY1, right? apply, well, LT, apply LT of LE of LT something HY1. Does that work? And now I'm going to prove that x minus epsilon is less than or equal to x minus some min. And now can I simplify this? Yes. I've got to prove that epsilon is less than, great. There. So, and now what's this one? Again, I've got to prove y is less than x plus epsilon, and I know that y is less than x plus something smaller. So this is LT of LE, I think now. Apply less than of less than of less than or equal to. And now let's try HY2. What does that leave me with? And great. And now let's simplify this. And again, this is left referal. So there you go. So there's some non-terminal simps for you. So one, sorry, left. What have I got to prove? I've got, oh, and it's just the same. That was a proof that y was in x. And now I've got to prove that y is in y. So this proof should pretty much do it. Let's try that. And now let's see. So it hasn't gone well. What's gone wrong? I should probably apply h delta 2 here. There. And now after the simp, I've got to prove, you see, now I need to prove the thing on the right. So this left should be a right. And this left should be a right. And we are done. So there's that. So now what? The filter axioms are now available. There's a standalone limit where the filter argument is implicit. Compare this. What does this say? The filter axioms are also available as standalone lemmas where the filter argument is implicit. This says, okay. I see. So the exciting news here is that that filter there is in round brackets, and that filter there is in squiggly brackets, which means that Lean will guess it. Because this was right. Because what's going on here is that filter dot sets of superset was created when the definition of filter was created. If we peek this, we can see there. When we made this filter, it generated filter dot sets of superset, and it made the filter. Explicit. We don't really want it explicit, and so we look at mem sets of. You can see the proof of mem sets of superset is just f dot sets of superset. Okay, great. And into mem sets just the same thing. Definition of tends to. Blah 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 blah. We'll practice using tends to by reproving the composition lemma tends to come from mathlib. Let's first use the concrete definition recorded by tends to def. So tends to def says what? So this is the definition. So we've got alpha and beta types. We've got a map from alpha to beta. We've got a filter on alpha and a filter on beta. And we want to say, and so this is the generic tends to predicate that was not in Bourbaki. This is somehow post Bourbaki. The idea is that a filter tends to another filter along a function, and this is the definition. If everything, and it's what you might guess really. For every subset of the target, if it's in the target filter, then its preimage is in the source filter. It's like saying a preimage of open set is open, but with filters. So there's tends to f L1 L2, and preimage comp says what? Preimage comp says, unsurprisingly, if I compose two functions and then take the preimage of a set S, it's the same as taking the preimage under G and then the preimage under F. Okay, great. So let's practice using tends to. So what's going on here? We know that A tends to B along F and B tends to C along G. A, B, and C are filters, and we need to prove that A tends to C along G composed with F. So clearly, what he wants us to do is rewrite tends to def at everywhere. there, and now we've got these for all statements. And now we could intros S and HS, and we've got to prove this, and now we can rewrite pre-image comp, presumably. Rewrite pre-image comp. We can, and so now we've got to prove the F inverse of something is in A, and we've got a method for doing that. We can use HF, so apply HF. And now we've got to prove that something's in B, and we've got a method for doing that as well. So let's apply HG. And now we've got to prove that S is in C, and that's an assumption. I think assumption should have an abbreviation. So that's the end of that. And now let's get functorial. Same statement as above, different proof packaging. So it didn't like this. Oh, okay. So it's going to prove this with map instead. So filter.map. Have we seen this filter.map before? Can we peek this definition? No definition found for map, but I bet it's there. What is going on with map? Where's map? That's comap. Where's map? Oh, is it up here? Section map. Bingo. So map seems to be this. If I've got a function from alpha to beta, and I've got a filter on alpha, then I can push that filter forward and get a filter on beta. And there's some definition. So what do? Pre-image? Oh, that's kind of interesting, isn't it? I see. So I think this says we've got so pullback F, this thing here, M is a function from alpha to beta, and so by using pre-image we've got a function from subsets of beta to subsets of alpha. So we've got a function from subsets of beta to subsets of alpha, and then we've got a load of subsets of alpha, and so we can we've got a function from subsets of beta to subsets of alpha, so we can pull back, and given a bunch of subsets of alpha, we get a bunch of subsets of beta. So there you go. So there's the definition. And I bet it's adjoint to comap as well. You can pull filters back. So map. And where's comap? There we go. And there's comap. So you see, given a filter on beta, you can get a filter on alpha as well. And presumably the theorem is that map and comap are adjoint functors. Okay. Let's find out what's going on here. So A tends to be along F, B tends to C along G. We've proved this already. And the idea is, I see, so the definition of tends to, what's the definition of tends to? Does it use map then? Oh, it uses map. Aha. It uses map. So I've got to prove, so what are we trying to do is we've got this filter A, and if we push it forward along the map G composed with F, we've got to prove that it's we've got to prove it's less than or equal to the filter C, and this is a weird less than or equal to, right? This means that everything in C is in A. So now what's going on here? Map G composed with F is map G. This will be called map comp, presumably, by rewrite map comp. Did that work? No. Unknown identifier. Is it map.comp? No. Oh, you've got me. I know, let's find it. By library search. It's having a good think. It's having a really good think. Oh, is it? Okay, maybe it's going to be called map. Oh wow, library search is letting me down here. Library search is still thinking. Curses. Let's try by rewrite map. I like the idea of map. Is map a thing? There we go, map. That's exactly what it is. So that's map. And now this will be map G something is less than or equal to map G something. So presumably I have map FA let's do this one. map GB less than or equal to C. This should follow from this, right? This should be the definition, in fact. Can I put HG here? Can I just put exact? There you go. It's exactly HG. It's definitionally equal to HG. And so now this thing here, so HF is the same that map FA. So maybe we can do this by simp HF. Oh, I didn't like it. That's a bit annoying. So what we need here is that if x is less than or equal to y, then map gx is less than or equal to map gy. So is it? Is there a map mono? Is that a thing? There's a map mono. So maybe it's map mono something. Can I get away with that? No. How annoying. Map mono. Map mono. I just really want this to be. Should I put more dashes? No. So this says curses by. Let's try this. Let's apply map mono. Sorry. Does this work? This has worked. Great. And now this is exact HF. There. So there we go. There's the proof of this. I'm sure I could have done better than this. What is map? Can this be map? Can this just be this? It can. But this thing here, this should be map mono HF. Why isn't this just map mono HF? This must be close. Oh, this is fine. This works great. So there you go. Turn mode for the win. Now let's focus on the pullback operation, comap, which pulls, given a filter on y and a function from x to y, we get a filter on x. And so here we can see the definition. Aha, so comap is slightly more complicated than map. You're in the comap if you contain an element of the pre-image. Fair enough. It also helps to record a special case of one implication. If you actually are an element of the pre-image, you're in the comap. The following exercise, which reproves comap nebot if, can start using this. So what have we got to prove here? We've got a filter on beta. We've got a map from alpha to beta. And if the pullback is not bot, then for all t and f, there exists an h such that m of a is in t. I don't really know what this says. Comap is not bot. Bot is the smallest filter, so that's the one with the most sets. So that says, well, let's figure out what's going on here. We could, what does this say? This is an if and only if. So maybe we should rewrite this. Let's take the hint. Let's rewrite this. It didn't like it, so let's rewrite it the other way. Now what? We've got to prove. Let's see what the question is. We've got to prove that everything in the comap is non-empty if and only if everything in the filter itself has the property, that there's something in the image. Well, fair enough. I see, and the reason I see, do I have to split this? I might have to split this, you know. Let's be unprofessional. Well, I'll tell you what, actually. Before we start, let's just see if simp does it. Simp's having a good think, and it does not do it. It changed something. It unfolded the definition of comap. Okay. What's going on here? So intro H. and intros x and hx. So now we have a set in the filter, and I need to come up with something in the image of m which is in x, and presumably we're going to use this. So why don't we specialize h? We need a subset of alpha, and we've got a subset of beta, so it's going to have to be the pre-image, right? So specialize h, and then m inverse pre-image of the pre-image of x. That'll be a start. And so now we need to prove that this thing here is in this, and that will be this thing here, right? Yes. So we need to prove, so it's pre-image mem comap, pre-image comap hx. How about that? Oh, I didn't like it. Because I didn't put brackets. That looks good. So now I know that something is non-empty. So H is the hypothesis that something is non-empty, and that something is a subset of alpha. So it's going to be, so let's do cases H with AHA. There is my, and so now I've got an element of alpha, and I'm trying to come up with an element of alpha. So let's use that one. Use A, and now I've got to prove that MA is in X, and I know that A is in, this will be exact HA, presumably. I wonder if I could have done, can I do exact H here? Oh yeah. There we go. I took it apart and then I put it together again. So in fact I can do this, exact this. There we go, look at that. And now what's here? So now intro H, what am I trying to prove? And now intros X and HX. And now let's see what the question is. I'm going to prove that a set is non-empty. So what does that mean? I've got to come up with an element of alpha. Great, so I still need an element of alpha. So where am I going to get this element of alpha from? I have H, and I need a subset of beta. So I need to use H somehow. So I need a subset of beta. I've got a subset of alpha. So the only thing I can possibly use is the image of that, right? So let's specialize H, and now this. And now I need to come up with the fact that this thing here is in F. And what was this thing? Pre-image mem comap. Can I conclude? What does this do? You're in the comap if and only if something. Great. So let's rewrite that. Rewrite mem comap sets at wherever it was, at hx. What does that say? It says that there exists a T. Great, so let's do cases. Cases hx with tht. Let's keep going. Let's do R cases. R cases hx with t, ht1, ht2. Right, so here's lots of facts. And now this says, oh dear. Do you know what? Maybe this wasn't the wisest of moves. No, this is forced. Maybe this wasn't clever. This. Because you see, I do have another element of I could use H on T. And then I would get something which was in T. I see. I would get something that was in ha ha. Great. Let's use. Yeah, I think this is a much better idea. Let's specialize. Let's specialize H, and then let's use T, and let's use HT1. And now HT2 says that, you see now, great. So I'm there, aren't I? Because now I can do cases H with AHA. Now I have an element. Now I have an element of T, and because this is a subset of X, I have an element of X. So I'm going to use A. I'm going to prove that A is in X. And I have a method for proving that things are in X, and it's called HT2. So apply HT2, apply it, and now I'm going to prove that A is in the preimage of T, and I know that M of A is in T, so this will be exact HA. Goals accomplished. There we go. Properties holding eventually. The next exercise only needs the definition of filters and the fact that for all, ooh, fancy notation. For all filtery X in F, PX is notation for this. It's called eventually and it won't be needed below. What? We only need this fact. Given two predicates are natural numbers, Pn and Qn for n large enough if and only if Pn holds for n under. Yeah. Pn and Qn holds. Aha. And Qn holds for n large enough. Great. That's what we've got to prove. Okay, great. So that's just, this is just the statement. Oh, it's an if and only if. So this says the sets corresponding to P and Q, the sets corresponding to P and Q, oh, I'm going to have to split this, I think. Because you see P and Q are maps to prop, so they correspond to subsets, and this says that the intersection, right, so this says that the intersection of those two subsets is in intro H. The intersection of those two subsets is in, and so now I have to prove, so split, and so now I need this axiom that says I now need the PX intersect, this says that this is in the filter, it says that P intersect Q is in the filter, and I need that P is in the filter, but that P contains P intersect Q. So I should apply, what's it called? Where's my definition of, have I got this over here? It's called sets of supersets. I'm going to apply sets of supersets. Apply sets of superset. I see. But now I need to say what the filter is. So what was that called? Patrick told me this. Mem sets of superset. Mem sets of superset. There. And so now why don't we give it H? Let's see what happens now. And now, who knows what this, so maybe I should do this properly. Right, we're doing it properly. So what's going on here? What's going on here is that, oh, what does it say? I think it says that it says that PX and QX implies PX, doesn't it? So P and Q, I mean, this is logic. Let's try CC. That's a good logic tactic. Show PX. Oh, do I need to intro it? Have I not got an X? Intro X. Bingo. And so now this says, yeah, so surely CC does this. Great. And now here, It's just the same proof, right? We can do this. There. There. And now we've got the sorry the other way. Does this type? No, I've done something wrong. Oh, have I finished the proof? I don't think I finished the proof. Bing. Ah, I see. Here we go. Yeah, I thought we'd only done one way. And now this way says that if P is in and if Q is in, then P intersect Q is in. So this is apply, whatever that other thing is called. Intersets. Is it mem intersets? Is that a thing? Into mem sets. Let's apply this. Apply into mem sets. And what have I got? What's even the goal? Oh, I need to do intros. Rintros HPHQ, comma, apply into mem sets HPHQ. How about that? That does it. Lovely. Topological spaces. So I only did this because Jason was asking if we could do topological spaces, and we've only just got to them and there's 5 minutes left. Oh, ArtMV says, can we do this? And the answer is yes. Thank you very much. He thinks it looks ugly. He must be a computer scientist. Code duplication. I've noticed that irks computer scientists. Did I ever see that thing there? Maybe that looks ugly to you as well, ArtMV. But you see, those aren't quite the same because there's this left and this right. So you have to be a bit cleverer there. What are we doing? Topology. So X and Y are topological spaces, blah, 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 blah. Continuous F says, yeah. Each point of X has a, the neighborhood filter. This is N of X because it's a topological space. It's a proper filter. Asking for continuity is the same as asking for continuity at each point. Yeah, so isn't this lovely? F is continuous. The definition of continuous, you can see the proof of this is REFL, right? The definition of continuous is that the preimage of an open set is open. But then they prove that F is continuous if and only if the neighborhood filter on X tends to the neighborhood filter on F of X along F. And this presumably is not remotely REFL. If I look at the proof, let's look at the proof of this. This will be, yeah, you see, this is some work. So right, the topological structure brings operation on sets. We have closure array, interior array, frontier array. Yes, closure array, great. Closure is the favorite, it's the best thing. A is in the closure, if and oh, so there you go. This is the nice definition of closure. When I'm in the closure of a set A, it means for every element of the neighborhood filter of little a, so for everything that contains an open neighborhood of A, it must meet capital A. Reproving mem closure if comap nebot. Okay, blah, blah, blah. First, let's review sets and subtypes. I know all about those, so let's press on. So why am I in the closure if and only if comap nebot? And so presumably he wants me to use this. Let's rewrite this. So now I've got to prove, let's see if the simplifier does it. Looks like the kind of thing the simplifier might. It doesn't do it, rotten luck. Okay, so we've got to think. So what's going on here? We've got to prove that everything in the neighborhood filter meets A if and only if co-e is the coercion. What is this coercion? It's a map. I see. The coercion is the map from A to X. And what are we? Am I supposed to use things I've used already? I wonder. We proved There's this comap something something nearby. Let's do it's comap nebot if. Let's try rewriting that. I'm going to see if I can do this without ever. Let's rewrite this. There. Now they're both statements about for all t blah blah blah. You see, this looks really good, doesn't it? Does the simplifier do this now? It doesn't. So, but this looks like, can I use congra? Congra primed. What's you see, I've got to prove that for all t blah, if and only if for all t blah. And so that feels to me, so it would suffice to prove that for all t blah if and only if blah. So what's that called? I can't remember what this is called. Example. Let's just work this out. So I've got, let's have x a type, and I've got p from x to prop. P and q from x to prop. There. And what I need to know for all, and then I've got a hypothesis that says for all x in x, px if and only if qx. And what I want to deduce from that is for all x px if and only if for all x qx. There, and this should say for all. And that should be, you see, because this is the thing I want to apply next. And that will be in the library, hopefully. So there we go. It's called for all congra. Of course, it's called for all congra. Let's apply for all congra. Did something happen? Oh, it did. Great. And now let's intro. Now let's intro y. And now let's apply for all congra again. And now let's intro hy. And now let's see what we've got. So now we've got to prove. Yeah, thanks, Xing. I've found it in the end. I've shown my method for finding these things. Just write down what you want and then use library search. Now we've got to prove that something's non-empty if and only if there exists something in it. Does simp really not do this? Come on, simp. Oh, come on. Really? Oh, but he gave us a hint. What was this non-empty? He gave us a hint about non-empty. What was his hint about non-empty? I thought he told us about how to prove something was non-empty. Oh, fair enough. Oh, no, there it is. It's that. Is it, in fact, is it exactly this? What was this? Oh, this is, maybe this is exactly this. Let's try library search. There you go. And indeed it finds the lemma that Patrick told us about. So that's the end of that. And I've gone on for an hour. I've only got 3 left. Okay, well, I'm going to stop now and I'm going to go to the, you know, I'll finish these on the Discord. But thanks for watching. There you go. There's me muddling through filters. I mean, lean isn't that difficult, really, is it? When you know, I don't know. It's good fun, but it's difficult. Okay, I'm out of here.